Hi, you guys. I'm a little slow getting the regression material up there. Sorry about that. I hope everybody is doing okay and hanging in there. You know, it's been a lot of big changes, but hopefully this really shouldn't impact our class too much. Everything's online, but hang in there and just do the best you can, and we'll all get through it. Anyway, so I already have my data set open, and you want to follow along in the assignment. I've got it listed out here in R, and there's an answer sheet. So this week we're going to look at simple regression, and basically that word regression, all it really means is fitting a model to data. And in this entire course, there's really only one model that we're talking about, and that's a linear model. And as you do the reading, you'll see that it's the basic structure of a line that we learned in the US in first year algebra. We learned that y equals mx plus b. M is the slope, and b is the intercept, and that's the basic format of this formula that we're working with. And you'll notice I had you skim the reading for field. We're going to look at it a little more closely next week, but just kind of get an idea, get the basic concepts. What we're doing here is kind of the application, and I would focus more on the application than the theory. That chapter 9 is a bit dense, and it really takes some time to pick apart. And by some time to pick apart, I mean go back and reread the chapter later on. Don't worry about memorizing everything in it. There's a lot there to know. I was lucky when I went through my statistics courses, and I was asked to be the teaching assistant for that course. And I can regurgitate information for tests, but I really did not feel like I had a great grasp on it. After that first year, I was actually kind of worried that somebody might actually ask me to do some statistics without being an example in a book. And so because I was a teaching assistant, I sat through those lectures for a couple more years, and they started making a lot more sense after 2 more years. But unfortunately, not everybody gets that chance to spend that much time on it, but really it takes that much time to really get it straight in your head. So I'm just warning you up front that, focus on the practical applications, and if you're really interested, go back and read more later. So we're going to use Jamovi again. Here's the modules that we've been using. We're not going to get into too much of those, but I'm just going to leave them there because that's what we're always using. So you should pretty much have that there. The scatter is the one that we will use today, but you should already have that installed. Here's our regular data preparation steps. We're going to look at data accuracy, make sure that we know the level of measurement for each variable and that they're correct in our data set. There's no spelling errors in the groups. There's just nothing in there that's weird. You don't have a blood pressure of 300 over 200. Nobody's 10 feet tall. Those kinds of things. Look for missing data, look for outliers, and we'll talk more about statistical assumptions. But I really want, at this point, memorize these steps, and even if you aren't a statistician, if you go look at data for something, you should go through these basic steps before you summarize data and give to somebody, because I can't tell you how often people just jump in without even checking the quality of what they have, and they get means and standard deviations without really checking things out, and they can be totally off with just a couple little mistakes in there. So I think if there was something you learned from this course, always do this stuff first before you do even basic stuff like running percentages and averages, because there are so many errors that just get passed on through and bad information. So we can avoid those kinds of things. So if you haven't figured it out by now, these steps, I'm always going to have them there, and you should pretty much fill these in and keep it for your next week, because it's going to be the same stuff. And if there's things that you're missing, add it in there and make this a nice list so that you have something to go back to and work with. And the description and field was not as good as this. I pulled this from some of those videos that were early on in this semester that I made optional because it's more comprehensive, but it's a good list to follow. So I wanted that reorganized a little bit from what you have in field. So let's go look at our variables in this data set, and then look at StatCat and see what it says to do. So I already have this album sales data set open, and that is saved in your zip file right there. It's also in field data sets if you download those. So if we go to data, and we can just take a look at these. So this first one is adverts, which is advertisement, and he's using an example for album sales. And this week we're really going to look at two variables. We're going to look at album sales and how much is spent on advertisement. So adverts is advertising budget in thousands. So 985.685, that means they're spending 985,000 pounds. This is 10,000 pounds, and I believe these are all pound numbers in pounds. It's probably a made-up data set, but he is from Great Britain, and so he does his things in pounds. It's continuous. This is money. Zero really means zero. If you were going to pick your level of measurement, I'll give you a second to think about that. Pause here while you think about it. Okay, time's up. That would be a ratio level of measurement. It has a real 0 point. We're talking about money. Zero means zero. When you got zero, you have no money. So that's a ratio, a very concrete measurement, and it's continuous. As we can see, we have decimals here. Sales, this is number of record sales or album sales, and that is a concrete measurement also. So zero means no sales, and that is also ratio, and that's correct in our data set, and that's all we're going to look at for a simple regression. Let's go ahead and go to analyses and go to data exploration. Well, we can just take a peek because this isn't a huge data set, so let's just take a little skim through. And as I scroll down here, I do see some numbers on the left are a little larger, but you know, nothing is crazy. There's not like 10 billion in any of those. I don't see any missing values in any of these. So, but this is 200 observations, so it's getting to the point where some descriptive statistics would be a little easier to absorb than just looking over the actual numbers. So let's go ahead and move adverts and sales over to our variables box. And under statistics, we have mean and median checked. Let's go ahead and get standard deviations, and let's get skewness. Sometimes I like to look at skewness. Let's go ahead and get our Shapiro-Wilk for normality test. If you're in SPSS, you're going to get a Kolmogorov-Smirnov, but Jamovi and R use this Shapiro-Wilk. And under plots, let's go ahead and get some plots for each of those variables. Let's get, these are continuous, so take a second and think about what kind of a plot you're going to get here. We're going to do a histogram and a box plot. If these were categorical variables, like they're dividing people into groups, we also call those a factor. We would get a frequency table instead, which we skipped over up here, but we'd get a frequency table and skip the mean and standard deviation. And we would get a bar plot, but these are not categorical variables. These are continuous, so we're getting means and standard deviations for descriptive statistics and looking at histogram and box plots for our descriptive plots. I'm going to go ahead and get this QQ plot here. And so we can see under adverts, we have no missing data under either variable. Means and standard deviations. So the standard deviation is almost as big as the mean for adverts, so it's fairly spread out. Not quite as spread out for sales. Got a good range on both of those. So skewness and standard error of the skewness. If you remember when we're looking at normality, skewness is the one that really counts. And we take this skewness and divide by the standard error, and we have 0.85 divided by 0.17, and that is definitely over 2. So I would be a little concerned about the normality of my adverts variable. It's not really normally distributed. The saving grace here is we do have 200 observations. So that's a nice large sample size. If you remember, you want to be a large sample size is usually 30 and above when we're doing statistics. So we're above that. So normality isn't gonna kill us here, but it definitely is not normally distributed. Sales 0.04 divided by 0.17. That's definitely well below 2. Although when we look at our significance test for normality, they both come out as significant. Adverts is definitely significant, and sales is still below 0.05. And that's one of the reasons I like to look at skewness divided by standard error of the skewness is Shapiro, Wilk, and Kolmogorov, Smirnov. Sometimes they can be a little bit conservative and give a significant result. We do have a large sample size that impacts that. So I will look at those, but I kind of rely on skewness divided by standard error of the skewness less than 2 is my thing when my judgment if I really get concerned about my normality assumption. So sales doesn't have such an issue, but adverts does, but we have a large sample size, so we're okay to continue on. If we really wanted to, so we could transform the data, and we haven't talked about that a lot. You can read about it. Sometimes if you take the log or the square root, you will make a variable a little more normal looking, and that helps meet assumptions. Look at Field on page 291. He gives some alternatives if you violate assumptions in the figure 9.10. We're not going to get into many of those, but just be aware there are some alternatives. Transforming your data so that it is more normally distributed is one of those options. Makes the interpretability a little more difficult, but it is something you can do. There's our histogram, and there's obviously outliers there. This is not, just skewed to the right. We can see on our box plot, we do have some dots up there for outliers on our box plot. And our QQ plot, you can see that things leave that normal line there. On our sales, not as skewed as our adverts variable. Again, no outliers there, and you see those dots stay along that normal line quite a bit better. So there's our quick assumption, our quick just review of these variables. Let's go ahead and jump into StatCat. And we're looking at relationships and prediction. That's definitely what we're doing with simple regression, is we're trying to predict an outcome variable from a predictor variable. And our dependent variable is going to be album sales. And our independent variable, we're only going to use one. We're going to do adverts. And we looked at Pearson correlations before, but we're really interested in doing a regression analysis, and it suggests that. So again, you have the luxury of this nice tool in Jamovi to help guide you when you're planning analysis. As you can tell right here, there's really no reason to get to the end of a study and find out you didn't collect the data that you needed to. You can plan this out ahead of time. Think about what you might want to collect and how you might measure it, and you can put those levels of measurement and variables, samples, into a tool like this, and it'll tell you what analyses you can do. And you should always plan this out before you collect any data on a study. So again, that's another piece of good advice. I can't tell you how often people get lazy about that and they don't plan ahead, and then sometimes there's problems. So when we have variables in, and we're going to do a regression, we really want to look at scatter plots first. And since we have a continuous predictor and a continuous outcome, that's a continuous independent variable and a continuous dependent variable, we're just going to run this one scatter plot. Next week, when we look at a couple more variables, we will go do a scatter matrix. But let's go ahead and put adverts in the x-axis and sales in the y-axis, and let's get a regression line in there. And what we really are wondering is, do we have a linear relationship between these two variables? And pretty much we do. We see we have a lot of spread out here at the bottom and not so much at the top, and that's kind of violating one of our assumptions of homoscedasticity. Again, we could transform a variable and try that, but we're not going to worry about that with this example this week, because we're just going to learn how to do our basic regression. So there's our scatter plot. Since we do have a linear relationship, we're going to go ahead and move on to do our regression analysis. So now we can go to regression up there in analyses, regression, and linear regression. And our dependent variable, again, is album sales. And we've seen this word covariates before. Basically, that's a continuous independent variable, and we're going to pick adverts as our independent variable. It's a covariate, meaning it's continuous. It doesn't divide people into group. We've seen that word factors. And yes, you can do regression with grouping variables. We'll talk a little bit more about that later, but we're not going to do that this week. Under model builder, you'll see that adverts automatically gets put into this block, and we will go with that. You can actually do more blocks and put things in order, and we'll talk more about that later, but nothing this week. So no changes under model builder. Reference levels is when you are working with categorical variables, and we're not doing any of that this time, so we can bypass that. Assumption checks. Let's go ahead and get Shapiro-Wilk and look at these QQ plots and residual plots for some assumption checks. Model fit. We have R and R squared. We're going to go ahead and get adjusted R squared. It's not great utility for us because it's an adjustment that gets made when you have multiple independent variables, but let's go ahead and check it because we're going to definitely look at it next week, and it's good to get used to using it. And we're going to select this overall model test, this F test, which is an ANOVA. Under model coefficients, we're going to go ahead and check the ANOVA test. We're actually going to see that this and this overall model test give us the same results, but let's go ahead and check the option. Under the standardized estimate, we definitely want to see our standardized estimate and see the confidence interval. And under our estimate, which is our non-standardized estimate, we're going to also select our confidence interval, and we won't have anything under estimated marginal means. So probably a good thing to look at first before we jump into assessing our regression is to take a look at our assumptions first. So we have our normality test. It's not significant. And again, we looked at our skewness divided by standard error. The skewness didn't have a problem, so we're pretty okay with that. There's our variable, and it's not too bad. So these residual plots, and it'd be kind of nice if there was actually a line here at 0. And what you're kind of looking is, do the numbers above the line and the numbers below the line, are they pretty even? And we do see that down here towards the lower end, they're more spread above and below than they are here at the upper end. So we do have some issues with our residuals here. Again, I'd probably transform the data, but we're not going to go into that. But I just wanted you to be able to look at this residual plot, and you can see that around 0 that it's not the same how it's spread above and below that on those residuals. Here's the sales residuals, and you can see that those are not spread around 0 evenly, and same thing with adverts. So we know we have some issues with our normality assumption here, and we could play with some transformations, but we're not going to go into that. We're just going to move on to looking at our regression information. And let's just take a peek at our answer sheet. Okay, you're going to talk about your data preparation steps. I did list on this answer sheet, field page 291. He's got a nice figure there, figure 9.10, kind of going over the steps of conducting a regression. And we already are at the point that we knew we were going to do a regression, but in our null hypothesis significance testing process, these things would have been done beforehand by deciding on our research questions, determining the data collect, and we've already had that done for us because we have a data set. So the null and alternative hypotheses. So let's go ahead and take a look at this regression output and what you're actually going to see here. And so you'll notice that there's a section for p-values here, and there's actually several sections that have a p-value. Anywhere that you see a p-value, you've done a statistical test. So since we're seeing several spots where there's a p-value, that actually is telling us that there have been several tests conducted, and each one of those is going to have its own null and alternative hypotheses. So probably something that helped me the most whenever I thought of regression, and this is true for linear regression, and this is true for other types of regression if you ever go on to study other types of nonlinear regression, is there's really two main things you're looking at. You're looking at, number one, the model overall. How good is the model? And there are some numbers here to just tell us how good is the model. And then the second main thing you're looking at is the parts of the model. Which parts of the model are the best? Are there any parts that are really effective, or are there any parts that really aren't effective? And right now this week we're looking at a very simple model, meaning that there's only one predictor variable. And next week we're going to look at multiple regression where we have more than one predictor variable. So let's look at the model overall numbers first. So I'm up here on this model fit measures, and we have an R and an R squared. And you'll see this is a capital R. Last time we looked at Pearson correlations, and we looked at a lowercase r. And a Pearson correlation was the relationship between two continuous variables. This big R is very similar, and it's a related thing, but we're looking at what is the relationship of the predictor variables with the outcome variable. And right now, when we will actually run a correlation, and maybe I'll go run that correlation right now, we only have two variables. We have advertising budget and record sales. And I'm going to go back to regression and do a correlation, and let's put in advertising and sales. And when we get that correlation, we see it's 0.578. When we go back up and look at our regression information, this big R is 0.578. We only have one predictor and one outcome, and so the relationship between the two matches the Pearson R. When we start adding more variables in, you will see that this big R does not match any one of the Pearson correlations between any of the pairwise correlation coefficients. Very rarely would you ever see. I've never seen one that actually did, but that would be a very different case. R squared, we looked at that coefficient of determination before, and when we square R, this is the proportion of shared variance between the two variables. And if we change that to a percent, we would know that our advertising budget is associated with 33.5% of our album sales. So it's not 100% by any means. So obviously you can spend a lot on advertising and not necessarily sell a lot. So it's not it's not the only thing that explains it, but it's a pretty significant contributor there with 33%. We went ahead and got adjusted R squared, and we'll talk about that. When you have a lot of predictor variables, then this R squared number can get inflated and artificially high. And so you'll see that 0.335 is really close to 0.331. The more independent variables, the lower this adjusted R squared would be, and the more I would go with adjusted R squared because it's more realistic in telling us how much of our dependent variable we can explain with our independent variable, or what the association is. So that's one part of the model overall, is this proportion of shared variance. And when it's just two variables, I'd go with R squared. If it's more than 3 or more, I'd probably go with adjusted R squared. So the test, here we have an overall model test. And we've seen F statistics when looking at ANOVAs, and we have a p-value. And what this is testing is a model where we don't have any predictors, just the intercept, against a model where we have our one predictor, and our null hypothesis is always some form of there is no difference. So in this case, it would be there is no difference between an empty model and a model with our single predictor. And the alternative hypothesis is there is a difference. And we can see that our p-value is less than 0.001, and that is significant. So we would reject the null, and we'd say there is a difference between our model with no predictors in it and our model with a single predictor. So our predictor model does better than just no model at all. You'll see that we checked the box for this omnibus ANOVA test, and look at that. Those numbers match exactly what the F statistic and p-value were. This just gives us our sum of squares and degrees of freedom, and Field does a nice job of going through the math for that. We don't need to memorize that. Just be aware that your first test of the model overall is this omnibus ANOVA test, or the overall model test. It's the same thing. We get an F statistic and a p-value, and it is significant. So we seem to have a good model. And then we're going to go look at our parts of the model. And we have an intercept, and then we have a slope. And since we only have one independent variable, we're going to have one variable here. And you'll see that you kind of have to get used to looking at these tables, and there's kind of a non-standardized part, and then there is a standardized part. And when we look at the non-standardized part, the first thing we're going to look at is the intercept. And what that is if our advertising budget were 0, what would be our sales at that point? And this gives us that value, and here it is 134.14. We could round that up to 134.14. And that is our value for sales when our advertising is 0. But of course, it's not 0. So then we wonder, how much do things change as advertising changes? How much does that impact sales? And the way you interpret this estimate for advertisement is for every, what you would basically say, and what I'll just memorize to say, is for every 1 point increase in advertising, we see a 0.096 increase in sales. So what that means is you would start at 134.14, and then whatever your advertising amount was, so say it was 100,000, then you would multiply this number by your 100 and add that to this estimate, and that would let you predict what are your sales going to be from any amount of advertising budget. So Field does a nice job of explaining the prediction equation, and really these non-standardized parameter estimates are what you use to create your prediction equation, where you use the independent variable to predict the dependent variable. And on page 294, he kind of explains how that works. So that's the main thing that you're going to look for. And then, of course, each part of that model gets its own little t-test. And so you'll see each line in this output, the intercept, and each independent variable. In this case, we only have one. There's a t statistic and a p-value. And from doing independent t-tests, we know that when t is going over the value of 2, it's pretty much going to be significant. And not surprisingly, this p-value for the intercept is significant, and the p-value for the adverts variable is significant. And what that tells you is that that part of the model is important to the model. That helps you to accurately predict the outcome variable from the predictive variables. So we see that the intercept and the slope are both important parts of that model. And we checked that we wanted our standardized estimates. Maybe I can make that a little wider so we can see more at the same time. There we go. And remember, when we standardize, when we get z-scores, we take a value and we subtract the mean and divide by the standard deviation. And what that means is that the average ends up being 0, and then the changes in there are in standard deviation units. So our intercept is kind of where our mean would be, so we're going to go to 0, so there's no estimate there. And then our adverts, that's our slope, and not surprisingly, we only have one independent variable, one dependent variable, and there's that 0.578, which matched our correlation. So when we only have one variable, our standardized estimate is the correlation between adverts and sales. So the non-standardized parameter estimates are for creating our prediction equation, and the standardized estimate, when we only have one variable, that is the correlation between our independent and our dependent variable, or the strength of the relationship between our independent and dependent variable. And we will see next week, when we start adding in more independent variables, the non-standardized numbers are each in their own units. So adverts, those are going to be in pounds, and there can be other types of things in other types of units. You can't really compare those things. Those are apples and oranges. Different types of things have different units of measurement, and the numbers you can't really compare. But when you standardize them, you're in standard deviation units, and then you can compare them. And this standardized parameter estimates will become really important for us to know which variables in the model are carrying the most weight, which are doing most of the predicting. But we won't look at that now. We'll just look at that next week. There was our assumption checks. Shapiro work we already looked at with the QQ plots. These were the parts of the model, and since we have a p-value, there would be a null and alternative hypothesis. The null would be that the estimate is no different from 0, basically meaning that the estimate is that variable is not important. The alternative would be that it is different from 0. And same thing on both of those. And you'll see that when we look at this confidence interval, 119 to 149, the value of 0 is not within the confidence interval, so not surprisingly, it is significant. Same thing on our adverts, even though these are less than 1, we'll see we're going from a value of 0.07 to 0.15, and the value of 0 is not within the confidence interval, so it is statistically significant. So looking at the confidence interval is another way that we can look at those tests and get an idea of how precise our estimates are on these things, how much range there is in there. Okay, let's go back and look at our answer sheet. So we know we're going to use alpha 0.05 as our criteria for rejection. We know that in all cases, for the model overall and for the parts of the model, we rejected the null hypothesis because our p was always less than 0.05. And we talked about what that means. And so what are we going to report here? I would report our big R squared and our F with our degrees of freedom, which we saw on our output for our F statistic. And you can see it gives us, there's our F, there's our 2 degrees of freedom. That matches what we have down here on this table. There's our F and our 2 degrees of freedom. So 1, 198, and the F equals 99.6, and the P value is P less than 0.001. P okay. That would be for our model overall, and you would want to label that, and then you would want to add another line for each of your variables, and I would just do intercept, and we would want our estimate equals and T equals and P equals, and we would do standardized estimate, and of course for the intercept it's not going to have anything, but we would add another line for the adverts and include all that information and include the standardized estimate there, and those are the things that I would report there. But field, you can read how he would, I don't know if he put much in here about how he'd write that up. And that's probably good. You can read through if you want to see any more about that. I hope you have a good week, and hope you're doing well. And let me know if you have any questions, and I will see you or you guys in office hours online. We'll do online office hours if you want to attend that on Skype, our Skype appointment. All right, see you guys.